Due to certain circumstances, Dr. Balakrishna is unavailable today, so the technical sessions today will be presented by Dr. Amit Kumar Mishra and Dr. Santosh Kumar. I would firstly want to introduce Dr. Amit Kumar Mishra, who is an assistant professor of statistics in the School of Physical and Decision Sciences, Baba Saheb Bhimrao Ambedkar University, Lucknow. He has more than 18 years of teaching and research experience in the field of applied probability stochastic orders, stochastic aging, reliability theory, and redundancy allocations. He holds a PhD from IIT Kanpur. He is a lifetime member of Indian Society for Medical Statistics and the Indian Science Congress Association. The technical session presented today will be based on parametric hypothesis test. I would now like to request Dr. Amit to begin the technical session. Thank you.
Am I audible? Am I audible? Okay. Thank you, Avantika. And first of all, I would like to thank Dr. Gautam Kumar Sinha for inviting me in this workshop. So, my topic is parametric testing of hypothesis. So, I will share my slide first. I think it is visible to all of you. Anyone please confirm the slide is visible or not? Okay. So, what is my aim? Basically, the objective of my talk is to first explain what a statistical hypothesis is and how we can use it with the help of sample data and how we can test it. And then we will discuss the difference between null hypothesis and alternate hypothesis. We will explain the meaning of rejecting a null hypothesis, and if you do not reject it, what does it mean? And then we discuss about p-value, and then we will see some parametric test with the help of SPSS. So I start with a very simple example, and this is says that there has been a great deal of controversy in recent years over the possible dangers of living near a high level electromagnetic field. One researcher, after hearing all these tales concerning the large increase in cancers, especially among children in communities which are living near high electromagnetic field, and she decided to study the possible dangers. Uh, to do so, she first studied map giving the locations of electric power lines, then used them to select a fairly large community that was located in a EMF area. Now, then she spent time interviewing people in local schools, hospitals, public health facilities in order to discover the number of children who has been afflicted with any type of cancer in previous 3 years. And then she found that there had been 32 such cases. So in summary, she found 32 cancers of any type in previous 3 years, basically uh, for the children. And this data she has collected from a community which is living near high level electromagnetic field. Now, she then visited a government public health library to learn about the number of cases of childhood cancer that could be expected in a community the size of this one she was considering, because there must be some uh, base to compare. And then she learned that average number of childhood cancers over 3 year period in such a community was 16.2 with standard deviation 4.7. Now we have question: is the discovery of 32 cases of childhood cancers significantly large enough in comparison with the average number of 16.2 for the researchers to conclude that there is some special factor in the community being studied that increases the chance for children to contract the cancer. What do we mean by that? Uh, C is getting 32 cases of childhood cancers, and this is the data C is getting. And then there is a data available with the library, and that data was on an average 16.2. So we can see easily there is a big gap between 32 and 16.2. So mathematically, these two numbers are different and there is a big gap. Statistically, our question is whether this gap, which we are seeing 32 and 16.2, statistically, is it significant or not? That means this 32 is significantly large enough in comparison with 16.2 or not. So what do we mean by significantly large enough? Technically, we will discuss later, but you can say that, or is it possible there is nothing special and this number we have got by chance? That means this difference which we are getting, this is only by chance. So we have two things: whether this difference which we are getting, this is only by chance, or there is something special by which we are getting this difference. So this is one example. Another example, this is a research from Punjab. So all of you know that advances in medical care such as prenatal ultrasound examination now make it possible to determine a child's sex early in pregnancy. And there is a clear cut fear that in some culture, some parents may use this technology to select the sex of these children. You know that in India it is illegal, but people may use it illegally also. So a study, Booth and others in 1994, they have studied from Punjab, and they have reported that one hospital, there is 56.9% of 550 live births were boys. That means you can say that almost 57% of the live births were boys. So it's a medical fact that male babies are slightly more common than female babies. Slightly more. It is not 50-50%, but getting 57%. So they have studied that baseline is for this region where the hospital is located is 51.7%. So the baseline is 51.7%, and in one hospital uh, they have got 56.9%. Now question again is same: is there evidence that the proportion of male births is different for this hospital? That means, are you getting the difference? With this difference is because of hospital, or this is by chance? Again the same question. So these kind of questions we got many times. So people want to answer these questions many times. For example, does the use of cell phone is associated with developing brain tumor? Does Vioxx increase the risk of heart disease? Vioxx is a tablet. Has teenage smoking decreased in past 5 years? Is the global temperature increasing? Or all of you have seen, at least in India, the Cadbury ad that kuch meetha ho jaye. Actually, this ad increases the sale or not, or any kind of ad. Any kind of ad increases the sale or not. So if we want to answer these kind of questions, we have to use statistical hypothesis. We have to test the statistical hypothesis about the models. So that is the base why we are learning testing of hypothesis. So these are some examples which motivate us to learn. So what is the statistical hypothesis now? So see, if you give any statement about anything, that is called hypothesis. For example, if you say that uh, smoking is injurious to health, if you say this statement, this is a hypothesis that smoking is injurious to health. But if I want to convert this hypothesis in terms of statistical hypothesis, we must have some parameter. Some parameter means, what do you mean by injurious to health? So we say that average age of a smoker will be less than the average age of non-smoker. So that we mean by injurious to health. So when you say average age of a smoker, that means you have put a parameter. Okay, you are focusing on one thing. So this kind of hypothesis is called a statistical hypothesis. So whenever we test some hypothesis, we focus upon statistical hypothesis, and they are the statement about the nature of the population, and most often they are written in terms of the parameters. So what is our aim? Our aim is to verify, for example, this example, that smoking is injurious to health. So if you want to verify it, you see many smokers and you see many non-smokers and find out the average age, what average life was there, and compare it, and then you decide about whether uh, your hypothesis is correct or not. So so something is true or something is not true, we cannot find. What we will find, we will find whether whatever data we are getting, that data is consistent with the hypothesis or not. So that we will see. So what do we mean by consistency, we will see later. So this one example, again, with the help of example, I will discuss the null hypothesis. See, remember, there is always a confusion among the non-statistician mainly, that how to fix null hypothesis. So someone say null hypothesis is that hypothesis which includes equality. Someone says null hypothesis is that hypothesis which put status quo. Those kind of things. But technically, we are going to see what is null hypothesis. Okay, so this example, there is a tobacco firm which claims that it has discovered a new way of curing tobacco leaves, and it will result that mean nicotine content of a cigarette will be 1.5 milligram or less. That means there is a method by which, if you cure the tobacco leaves, mean nicotine content will be less. That means it will be less harmful if you use that cigarette. But a researcher is skeptical of this claim, and indeed believes that the mean will exceed 1.5. So researcher thought that mean exceeds 1.5. Companies claim that mean is less than or equal to 1.5. So since researcher is skeptical, he wants to disprove the claim of the tobacco firm. So I am emphasizing it. He or she wants to disprove the claim of the tobacco firm. The researcher has decided to test this hypothesis. So if you see the null hypothesis, this null hypothesis is written as H under as a subscript 0. We call it H0, or someone call it H naught. Mu less than or equal to 1.5. What is mu? Mu is just a representation of the mean nicotine per cigarette. It is just a representation. So what we are saying that mean nicotine per cigarette is less than or equal to 1.5. Remember, this was the claim of the tobacco firm, and researcher wants to test it. Remember that researcher wants to disprove it. So first line is, if a researcher wants to disprove something, that should be the null hypothesis. So in some books, you may find that null hypothesis is that hypothesis which we want to reject. Okay, so remember, you have to focus upon that hypothesis. You have to make that hypothesis null which you want to disprove, number one. And then there will be alternate hypothesis. Why there will be alternate hypothesis? If you are disproving something, you have to give some alternate. Okay, you are saying that mean nicotine is not less than 1.5. Then what will be the alternate? So I am here, alternate is very simple, it is greater than 1.5. Here alternative is very simple, it's just greater than 1.5. So remember, when you reject the null hypothesis, what you are going to conclude, so that conclusion should be written in terms of the alternate hypothesis. So here we write it H1 mu greater than 1.5. Okay. Now if we focus upon electromagnetic field example. Okay. Remember, in that example we observed 32 cancer childhood cancers and reported was 16.2. So what should be the null hypothesis? So the null hypothesis is there is no effect of EMF on childhood cancer. Why? Because we want to disprove it. We want to prove that there is an effect of EMF. That kind of situation is there. So this is your null hypothesis. There is no effect on EMF on childhood cancer. This I have written in terms of language, but we can convert it in terms of the parameters also. Now question arises, if I reject this null hypothesis, what will be the possible alternatives? So first alternative we may have, there is an effect of EMF. Second alternative we may have, there is an increase in childhood cancer. See, when you say there is an effect, the effect contains increase in childhood cancer as well as decrease in childhood cancer. So, but when you say there is no effect, so alternate may be there is an effect, there is an increase, there is a decrease. So we have three alternatives. We have three alternatives. Which one we should choose? Of course, we want to see whether there is an increase or not. So we should choose H1 star. There's an increase in childhood cancer due to EMF. But technically speaking, fairly speaking, all these four hypotheses are wrong. Why? Because your study was observational. If you remember, the researcher just has observed, interviewed the people, asked them. So that was an observational study. In any observational study, you cannot decide the factor influencing the cause. Here I am saying this, there is an effect of EMF. We have not studied effect of EMF. We have just observed. So the correct way of writing the hypothesis is there is no factor affecting the childhood cancer. This is the correct way. See, we have just observed. So we cannot say that this is due to EMF. We can only say that there is no factor affecting the childhood cancer. Alternate, we can say that there is some factor affecting the childhood cancer. There is some factor which increases the number of childhood cancer. There is some factor which may decrease the number of childhood cancer. So these are the alternatives. This is the null hypothesis. So remember that when you are doing observational study, you should not write down that there is an effect of EMF because you have not controlled anything. So there is this is the correct way of writing hypothesis. If you see the second example, a live male birth, remember that observed was 56.9% and reported was 51.7%. And what we want to verify? We want to verify that this particular hospital proportion is equal to the reported one or not. So the proportion P, now I have written in terms of the parameter. P is the proportion of male births. So I'm writing null hypothesis P is equals to 0.517. Then if you reject it, what can be the alternate hypothesis? See, alternate hypothesis will have again the three possibilities. P is not equal to 0.517. You are saying P is 0.517. If you reject it, you can say that P is not equal to 5.517, or you can say that P is bigger than 0.517, or you can say that P is less than 0.517. So it depends upon your aim of the study. Which alternate hypothesis you will choose depends upon your aim of the study. So remember that null hypothesis will be there which you want to disprove, and alternate hypothesis will be that hypothesis which is the alternate according to your target or your goal. Now, how to test this? So there is a test statistic. There is a test statistic. So what is test statistic? So basically there is a mathematical formula. Okay, so there is a mathematical formula. You collect the data, and with the help of data you find a number, or you use a formula and find a number, and with the help of that formula you decide whether you should reject the hypothesis or not. So that formula, that means it is a function of the data. So that is called test statistic. It is just like that if you are a teacher, you have completed your syllabus, and at the last you will prepare end semester question paper. So in your question paper you will not ask everything, you will ask something and you will leave something. So now question arises, how good your test is. So your test will be good if you cover whole syllabus, whatever you have covered, and your test will be good if you check the analytical ability of the student, if you check thought process of the student, if you check memory of the student. That means if you check everything of the student, then that will be a good test. So similarly in statistics we have a data, and then we find a function, we find a formula, you can say we find a formula, and with the help of formula we decide about the hypothesis. And that formula, you can say, it is a test statistic. Okay, now what is the critical reason? So when you find a formula, it will give you some number. So which number is going to reject the hypothesis and which number is going to not reject the hypothesis? Just an example, if you take 100 marks test, in every university it is different, but if I assume that 40 is the passing marks, so below 40 is actually excuse me, below 40 is actually critical to the student. If a student gets 39, 38, 37 or any other marks below 40, that would be critical for the student, because a student will get a F grade. So that reason, if any student's marks fall in that reason, that student will get F grade. That means he or she will not pass that exam. Similarly, we have a formula, that means we have a test statistic. Test statistic will have different values if you put the data. Now, out of those values, which are the values which are against the null hypothesis? So those values which are against the null hypothesis, they are called values belonging to critical region. Okay, so I hope critical region is clear. So in simple, we write down, if we represent capital C, our critical region, and if we write down Ts, test statistic, so we say that reject H naught if test statistic is in the critical region C. What do we mean by that? It is just put an F grade to the student if his or her marks is below 40. That kind of situation we are saying. Reject H naught, but that means put an F grade if his or her marks is less than 40. So 0 to 40 is actually critical region, excluding the 40 number. Do not reject. That means do not put F grade. Remember, do not put F grade. If his or her marks is more than 40, that means that does not lie in 0 to 40. It is exactly 40 or more than 40. So do not put F grade. Remember that. Do not put F grade means now student may get A grade, B grade, C grade, A plus grade, depending upon what is the grading system. So we are just saying this kind of thing. So in testing of hypothesis, we also have the same situation. I will show you with an example. For instance, in the tobacco example, you remember there was a new technique by curing the tobacco leaves, and if we assume that standard deviation is 0.8 and we take 36 cigarettes, that means there is a production of cigarettes based upon new technique, we randomly choose 36 cigarettes out of that, and we know that there is a standard deviation of 0.8. Then after some calculation, if we get this reject H naught, if x bar means sample mean, that means whatever you are getting from 36 cigarettes, you find out the average nicotine, and if your average nicotine is more than or equal to 1.72, you reject the null hypothesis. Otherwise, do not reject H naught. Now you remember what was your null hypothesis? Your null hypothesis was that mean nicotine is less than or equal to 1.5. So see the idea. There is a number 1.5. Someone claims that nicotine is less than 1.5. Now, if you show that it is 1.6, then someone says that, okay, this is a random sample, so this much of fluctuation is allowed. If you say that it is 1.65, they may say that it is because of random. Now, question arises, how much far you can go? So this says that if you go beyond 1.72, that means there is a 1.5. From 1.5, if you move towards 1.6, it's no problem. 1.7, no problem. 1.71, no problem. But if you cross 1.72, that shows that mean nicotine should not be less than 1.5. This is the idea. So this 1.72 is the boundary, and rejection region is crossing the boundary. So what is the rejection region? Rejection region is here, starting from 1.72 up to infinity. This is the rejection region. So this kind of situation is there. Okay, now you can ask how to find this test. So you have to not worry about these things. Every software has inbuilt idea. My aim is to explain you how to write down your null hypothesis, how to write down your alternate hypothesis, and when you apply a test and you get a conclusion, how to write down that conclusion. That is my aim to explain here. Okay, now this is the situation. If you focus upon 1.72, then if this is the normal distribution, and when you focus upon on 1.72, average will be bigger than 1.72. This probability is 0.05. That means it is a very small probability. Now you see the consistency, the meaning of consistency here. If the mean is 1.5, see the normal distribution, the mean is 1.5. So if the mean is 1.5, crossing 1.72, there is only 5% possibility. If mean is 1.5, there is only 5% possibility you cross 1.72. Now you see, company claims that mean nicotine is less than 1.5. So if mean is less than that, this crossing 1.72 will be less than 5%. So that means there is a very small possibility. That means if really company's claim is good, if whatever company is saying, if that is true, and you find out 36 cigarettes and the average crosses 1.72, that means it has only 5% chance. Now if you are getting something which has only 5% chance, then you will have only two things. Either whatever you are getting, if you accept that is it is good, so there is a very rare event which is happening. Otherwise, whatever assumption you had, and your assumption was that mean is 1.5, so that assumption is wrong. So either your assumption is wrong, or you are getting whatever is by chance. So here in statistics we say that our assumption is wrong. That means our hypothesis is we have to reject the hypothesis. That is the idea behind it. So you can see in the next graph, if I take 1.72 instead I take 1.7, so this probability will increase. So when this probability will increase, we say that it's okay, don't bother about the null hypothesis, don't reject it. And if you get 1.8, now you see that this probability is further reduced. It is less than 5%. So that means you are on the boundary. So if you are on the boundary, your mean cannot be 1.5. That should not be there. So this is called inconsistency with the hypothesis. So this getting 1.5 is inconsistent with the null hypothesis. Why? Because null hypothesis says that mean is 1.5 or less than that. So if mean is 1.5 or less than that, getting 1.8 is extremely rare. So it is inconsistent with the data. Okay, that is the idea. So the interpretation is rejecting of null hypothesis. You can see when you reject when your point lies on the tail. That means there is a very less possibility. Then you reject. So rejecting the null hypothesis is a strong statement, because you will only reject when there is a very less possibility. There is a small probability. Then only you will reject. So it is a strong statement. Rejecting null hypothesis is a strong statement, and it can only happen when your data does not appear consistent with the hypothesis. And that's why we focus upon null hypothesis, those null hypotheses which we want to reject, because rejection is a strong statement. So if you don't reject it, it is a weak statement and there will be no conclusion at all. That is the idea. So but whenever you do this, of course you may commit errors. For example, if you reject h0, actually h0 is true and your data rejects it, so there will be an error, and this is called type 1 error, and this is also called false negative. False negative means because something is correct and you are saying that reject it, so you are negating it and that negation is false. And type 2 error, if something is false and you are not rejecting it, so that is called false positive. This is just I can show that if there is a good student in your class and you prepare a question paper which fails that good student, so that means you have prepared a question paper which is extremely difficult. And if you prepare a question paper like that, the worst student of the class passes through that question paper, so your question paper is not very good. So that these are the errors in your question paper. So you have to prepare the question paper in such a manner that if there is a bad student in the class, that should fail, that should definitely fail, that question paper should be there. And if there is a good student, there is a brilliant student, they should get good marks. That kind of paper setting must be there. So similarly, testing is there. So we may commit errors. So what we do, whenever you have two kinds of error, we cannot minimize both of them. So what we will do, we will fix type 1 error. We will fix type 1 error means whenever h naught is true, we say that we will reject h naught at most 5% of times, or 1% of times, or 10% of times. So we are fixing that. So rejecting a true thing, we are fixing the boundary for that, and that is called level of significance. Okay, so our objective, I told you, our objective is to see whether h naught is consistent with the data or not. So level of significance, so we fix probability of type 1 error. That means we say that if someone is some hypothesis is true, our test should not reject that at more than 5% of times, or more than 10% of times, or more than 1% of times. That is called level of significance. Okay, so now question arises, how to fix level of significance? So remember, if rejection of the null hypothesis, the consequence of rejecting the rejection of null hypothesis, if the consequence is very dangerous, then your alpha must be very small. I give you one simple example. If there is a person and there is a court case on that person, that this person is a murderer. So in court, the judge consider the null hypothesis that the person is innocent. This is the null hypothesis of the judge. Okay, the person is innocent, because if judge assume that person is guilty, the person will definitely get some kind of punishment, because judge is biased at that time. So judge assumes that okay, person is innocent. Now person is innocent. Now you reject this hypothesis. Reject means judge rejects this hypothesis and give death sentence to that person. So now see the idea. If the person is really innocent, really, and he gets the death sentence, it will be a disaster. So rejecting h naught, when h naught is true, that means the person is innocent and you are rejecting it and you are punishing him with a death sentence. So the consequence is very dangerous. The consequence is very dangerous. In that case, alpha must be 0.0001 or less than that. And you all of you have listened somehow that leave persons who are guilty, but don't punish a person who is not guilty. That kind of situations you have listened. So one out of out of 1,000, only 1% should be that kind of situation. So alpha should be very, very small. So remember that when consequence of rejecting h naught is a severe kind of thing, your alpha must be extremely small. Okay, so this I have explained. Now what is p-value? P-value is basically gives the probability of getting that kind of data which you are getting, or extreme to death. So p-value is the smallest significance level at which the data lead to rejection. So for example, if p-value is 7%, so below 7%, you cannot reject the null hypothesis. That is the idea. So whenever your p-value is bigger than alpha, you will not reject the null hypothesis. If your p-value is less than alpha, you will reject the null hypothesis. Okay, so this is the p-value, that if h naught is true, p-value will be the probability of getting the data which you are getting, or extreme to that. That is the idea of p-value. So designation, I have already told you that if you are trying to establish a certain hypothesis, then that hypothesis should be alternate. And if you are want to disprove, that hypothesis should be null. Now you can see the same example, the tobacco company example. Now, for instance, if the tobacco company is running the experiment, means instead of researcher, if tobacco company runs the experiment, so what should be the null hypothesis? Now you can say that the null hypothesis may be same. No, null hypothesis may not should not be same. Remember that. Now, who is performing the experiment? The tobacco company says that mean nicotine is less than 1.5. So that means tobacco company wants to prove it. So it should not be the null hypothesis. Now our null hypothesis will be the reverse one. That mean is greater than or equal to 1.5, and the alternate hypothesis is mu less than 1.5. So see, the important thing is here. Same example is there. Example is same, but null and alternate are interchanged. Why? Because who is performing the experiment? If a researcher is performing the experiment, researcher wants to disprove the tobacco firm's claim, so that claim should be the null hypothesis. But if company is performing the experiment, then company wants to prove it, so it should be the alternate hypothesis. So the same hypothesis may be in the alternate, may be in the null, depending upon who is performing the experiment and what is the aim. So remember this example. This will give you the idea that null and alternate hypothesis may be changed. Now question arises, if I change it, the answer will see, the statistical tests are designed in such a manner, if you do this, you will get the right answer. So there is a mathematical theory behind it. I cannot go into that theory. So but believe on me that if you want to disprove something, that should be the alternate hypothesis. If you want to prove something, that should be the if you want to disprove something, that should be the null hypothesis. If you want to prove something, that should be the alternate hypothesis. This is the one line answer. The summary is that we will always have a parameter which lies in some region. Parameter lies in some region means, for example, if you say mean nicotine, so mean nicotine lies less than or equal to 1.5, and then will be alternate. That mean nicotine does not lie in that. So what we will do, we will fix alpha. That means level of significance. You have to fix it first. That means what type of error you want to commit maximum. So you have to fix that. Then you have to find a point estimator. Point estimator means, for example, in mean nicotine example, we have written x bar. That means the average. So that is our point estimator. And then find the distribution, because without the distribution, you cannot find the probabilities. Then you find the probabilities or p-value, and with the help of p-value or critical region, you find the answer. So this is the summary of data. So if there is okay, we'll discuss the question and answer at last. Now I will discuss some popular test. So one sample z test, see, usually in practice it is not there, because we have random sample from normal population, number one, and we are interested in testing of hypothesis about the mean, and we assume that population variance is known, which is such type of assumption which do not meet in practice. And sample size does not matter. That means sample size is small or large, that does not matter. The main thing is population variance is known or not. So for example, if you want to test whether mean height of Indian male is 6 feet or not, that kind of situation. But you know that you will not have population variance in that case. So if I assume that population variance is known, then I can use the Z-test. So what is the idea? Now see, this is a normal distribution. The hypothesis will be mu is equals to mu naught. Mu is equals to mu naught means you know that mean is this or mean is not this. So when you say that mean is not this, that means you have in alternate you have two possibility. Mean can be more than this or less than this. So in alternate, if you have two possibility, you in rejection region you will have two possibility. One is on the right hand side, one is on the left hand side in this normal distribution. So you see this graph, if you are between in these two numbers, which are I am writing minus z alpha by 2 or z alpha by 2, if you lie between these two numbers, hypothesis will not be rejected, otherwise hypothesis will be rejected. And what is the test statistic? Test statistic is root n x bar minus mu naught by sigma. So don't bother about this mathematical formula, just understand that there is a distribution. If you lie on the right hand tail or left hand tail, it will be rejected, otherwise it will not be rejected. That is the basic idea. Okay, now there is an example. It says that there is a particular star and it emits emits the rays, and we want to estimate the intensity. So they have said that standard deviation is 4 and it is suspected that intensity is 10. So 20 times it has been observed and the average of 20 values is 11.6. Now see, null hypothesis is that mean intensity is 10 versus mean is not 10. We calculate this test statistic, that means the formula, this is square root n by sigma mod of x bar minus mu. So you put n is 20 divided by 4. X bar means the actual which you have observed, that is 11.6, and mu naught which you assume, which is 10. Even you calculate, it is 1.79. Now see, this is not equal to, so 1.79. So when you draw the graph, you see there is a number 1.96. So 1.96, this number, if you cross this number on both the sides, okay, then you will have total area will be 5%. So that means your alpha is 5%. If you fix your alpha 5%, then the boundary point will be 1.96. And in that case, 1.79 will belong to, or will belong to this area. What I am seeing the orange color, I don't know others. So this orange color, for example. So this will not be in rejection area. This is not in the blue area. Okay. So this is not in the blue area. So that means you are not rejecting it. When you change alpha, you see, you change alpha, alpha is 10%. That means now you are ready to commit more mistakes. If you are ready to commit more mistakes, area will be large. You can see blue area is large now. And blue area is large. So 1.79 now comes into the rejection region. So you will reject the null hypothesis. So if you are ready to commit more mistakes, rejections will increase. Because what is alpha? Alpha is rejecting H naught when it is true. That means if something is true, you are rejecting it. So you are committing a mistake. So if you increase alpha, your mistake will increase. So if you just focus upon 1.79, the area will be almost 7%. So this is the p-value. This is the p-value. So p-value is the actual area. Remember, if you fix alpha, you will have a boundary. So those boundary are actually 5% or 10%. So those are not actual area. When you see the value 1.79, which you are getting from here, 1.79, and if you find out the area beyond that, that is called p-value. So here p-value is 7%. Now you can easily understand, if p-value is bigger than alpha, that will not be in the boundary. So you will not reject H naught, which is the first case. In first case, p-value is 7% and the alpha is 5%. So you are not rejecting it. In second case, p-value is 7%, alpha is 10%. So you are rejecting it. Okay, so now there will be one-sided test. One-sided test means if you want to test this kind of situation, mu is less than or equal to mu naught, mu is greater than. So now you can see in alternate hypothesis, you have only one side, mu bigger than mu naught. So your rejection region will also be on the one side. That is the idea, nothing more than that. Okay, that means in this case, you are finding on both sides. Both sides means if your alpha is 5%, you divide this alpha into two half. 2.5% on the right hand side, 2.5% on the left hand side. But in one directional, there will be whole 5% on the one side. That is the main difference. Now we come to the famous test, which is the T-test. So what is T-test? It is similar to Z-test, but the main thing is now population variance is unknown and sample size is small. So if you have a random sample from normal population and you want to test population mean, that means mean is 5 or 7 or something else, and population variance is not known and sample size is small, then we go for the T-test. Remember the assumptions, because assumptions are extremely important in statistics. If your data does not follow assumption, your conclusion may be wrong. So in the same situation, there will be T distribution instead of normal, and it is also symmetric. All other things will be same. The only change is in the test statistic, which is not root n x bar minus mu naught by capital S, which is sample follow, and this follow the T distribution. All other things are same. So I will explain this example with the help of SPSS. Okay, there is a software SPSS. I assume that you know the basics of SPSS. So with that assumption, I will explain this problem. Okay, now this what this say, historical data indicates that the mean acidity, that means the pH level of rain in a certain industrial region in West Virginia is 5.2. Okay, to see whether there has been any recent change in this value. See the language. Language is very important. What we want to see whether there has been any recent change in this value. So change means it may increase or it may decrease. Remember that. The acidity level of 12 rainstorms have been measured, and these are the acidity levels. Are these data strong enough at 5% level of significance? So level of significance has been fixed up to 5% for us to conclude that the acidity of the rain has changed from its historical value. So see the blue color sentence, to conclude that the acidity of the rain has changed from its historical value. So this you want to conclude. That means this is your alternate hypothesis. Okay. So what is your alternate hypothesis? Alternate hypothesis is mean acidity has changed. And from where it has changed? It has changed from historical value. And what is the historical value? Which is 5.2. So that means it is not 5.2 now. So this is your alternate hypothesis, that mu is not equal to 5.2, because you are saying that we want to conclude that it has changed. So it has changed means it is not equal to 5.2. So this is your alternate hypothesis. This is your null hypothesis. And how to perform this test in SPSS, I am going to explain that. So this is the screenshots I have already taken. So I have two options. One is I should go for the screenshot, or I will run it live. So what you want? I have shared the data with Dr. Sinha. He will share the data with you. You can play with the data. I will explain you here. Okay. So I will explain you directly. Someone is saying directly live. Okay. We'll see live. So for that I have to stop it and I have to reshare my slide. Reshare SPSS data. Okay. I hope now this is is shown to you. So this pH. So first thing in SPSS, there is a data view. So see, there is a data view. I have defined the name pH. This is a numerical value, and I have given the scale. Measurement scale is a scale, and just I have entered the data, all the data, 6.1, 5.4, 4.8 in a column. Okay, I have entered the data. So this is the SPSS. Now you just go and click on analyze. When you click on analyze, you will have many options. First option is report, second option is descriptive, third option is table, fourth is compare means. Yeah, actually we want to compare mean, so we have to stop here, and in that there will be a sub window. In that there is a one sample t-test. You can see one sample t-test, because you have single population, you want to use t-test, so you have to click on this one sample t-test. When you click on this, whatever variables you will have in your data sheet, all the variables will be here, all the variables. Since I have only one variable, it is showing only one variable. All the variables will be here. You have to choose, you have to select the variable of your interest. So you select pH and click on this arrow button. You see now pH is on the right hand side. This is called test variables. Test variables means which you want to test. Now what is the test value? Test value is 5.2. If you remember, test value was 5.2. We wanted to test whether pH is 5.2 or not. So that is the test value. If you go into the options, there is confidence intervals, all those things we don't want. So you just click on OK. So when you click on OK, this is the output. See the output. Focus upon this. This is the summary of the data. That pH, you have 12 observations. The mean is 5.667. Standard deviation is 0.9208. Standard error mean is this. And this is the test. So t value is 1.756. This is the t value. It has 11 degrees of freedom because you had 12 observations. It has two-tailed significance. So remember, you need two-tailed. Why? Because your alternate hypothesis was that mean pH level is not equal to 5.2. So you need two-tailed. If it is not two-tailed, you just take this number and divide it by 2, because t is symmetric. So it is this value is 0.107. So what it is giving you? It is giving you the p value. So 0.107, that means more than 10%. So your p value is more than 10%. Remember that your alpha was 5% only. That means you are ready to commit only 5% mistakes, and the p value is 10%. So it is bigger than 5. So you will not reject H0. So the conclusion is we are not going to reject H0. That is our conclusion. So you not rejecting H0 means you cannot say that it has changed. Remember that. If you are not rejecting it, that means it is not different from 5.2. So your claim, you cannot conclude that it is different from 5.2. That you cannot conclude. Okay. So okay, I should stop it here. I will share entire screen so that easily move to screen to screen. Okay. I hope now this I have covered. This is the conclusion. It would not be rejected. Now, two samples at test. Two samples at test means we have more than two populations. For example, you want to test mean height of male and mean height of female, of Indian male and female, whether they are same or not. That kind of situation if you want to test. So this again, the Z test is not very useful because we don't know. We assumption is population variances are known, and this is not a practical assumption. Again, the sample size does not matter. The formula will change. Now we write down mu x is equals to mu y. That means mu of first population, mean of first population is same as mean of second population. Mean of first population is different from mean of second population. Again, it will have normal distribution. The formula which you use, this is the test statistic. You take the difference between x bar minus y bar and then divide it by this, find out the value of this quantity and see whether this quantity lies in the critical region or not. If it lies in the critical region, reject H naught, otherwise do not reject H naught. That is the idea. So I am not going into mathematical detail of this. Okay. Now we will focus upon, basically we will focus upon t-test. So if we have independent samples from two normal populations and we are interested in testing hypothesis concerning the respective population means, that means we want to test whether two populations have same mean or not. Okay, we want to test whether two populations have same mean or not. But what is the assumption? Assumption is population variances are unknown. We do not know them. But remember, we assume that they are approximately equal. We assume that they are approximately equal and sample sizes are small. Okay, and sample sizes are small. So in that case, we can use t-test, and I will explain the example, then we will run this example in SPSS. So what we have 22 volunteers at a cold research institute caught a cold after having been exposed to various cold viruses. Okay. Now what we do, a random selection of 10 volunteers out of 22, we have given some tablets of vitamin C to them. Okay, all of you know that in cold, vitamin C helps us. Okay, so we want to test this assumption, whether vitamin C cures the cold or not, that we want to test. Okay, so out of 22, 10 volunteers randomly selected and we have given them vitamin C, and we have suggested them to take 4 times a day. The control group, that means other 12 volunteers, they were given placebo tablets that looked and tasted exactly like vitamin C, so that they cannot understand whether they are getting vitamin C or not, because psychology also play a role in curing human health. Always remember, psychology also plays a role. So they have given the same taste, same look kind of tablets, so that person do not know whether they are getting vitamin C or placebo. This was continued for each volunteer until a doctor, who did not know whether the volunteer was receiving vitamin C or placebo, doctor also do not know, this is double blinded experiment, decided whether the volunteer was no longer suffering from cold. So now they have checked whether uh, persons are suffering from cold or not. The length of time the cold lasted was recorded. So this length is recorded. First person 5.5 days or whatever, they have taken this much of time to recover, and they were getting vitamin C. First person who was getting placebo takes 6.5 time units. So these are the time units for persons getting placebo. These are the time units for persons getting vitamin C. What is our aim? Our aim is very simple. Do this data prove that taking 4 grams of vitamin C daily reduces the time that a cold lasts? At what level of significance? Now, the question tells you what should be the null hypothesis and what should be the alternate hypothesis. So it says that if you take vitamin C 4 grams per day, it reduces the time that a cold lasts. Reduces the time means taking vitamin C is curing your body in less time. Okay, that is the idea. So you can say that average time of cure of those persons who are taking vitamin C is less than the average of the persons who are taking placebo. So that is the parameterization of the language. So our null hypothesis will be mu p is less than or equal to mu c, and alternate hypothesis will be mu p greater than mu c. See, the alternate hypothesis, mu p means average time taken by persons getting placebo. So if you are getting placebo, your cure time will be bigger than the persons who are getting vitamin C. That we want to prove. This we want to prove. Is it or not? So this we want to prove. So this is the alternate, this is the null. So we have prepared the null and alternate hypothesis. Now we have to test this. We will go for the t-test. So I will show you this with the help of data. So I have data with me. Vitamin C. This is the vitamin C data. Now see how to enter the data. Here, this is important, how to enter the data. Since we have two populations and they are independent. They are independent means volunteers who are getting placebo, they don't have anything with the volunteers who are getting vitamin C. So they are independent populations. So for independent populations, if we want to compare in SPSS, we have to prepare a group variable. So we have to prepare a group variable. So I have defined a group variable. Group variable will be nominal. Remember that it will be nominal. Nominal because it will only indicate whether the person is getting placebo or person is getting vitamin C. So it is a nominal variable. So you have to define group variable. And in that I have defined that 0 indicates placebo. That means if there is a 0 in data, that means the person is getting placebo, and 1 is getting vitamin C. That is the thing. So after defining these things, I have entered group. If you see 1 means, see, you can see vitamin C, vitamin C, vitamin C. So first 10 items, first 10 persons are getting vitamin C, other 12 persons are getting placebo, and these are the duration. These are the durations. Okay. So if I change it in numbers, 111 000, so 111 implies vitamin C, 000 implies placebo. So this is the data, how you enter the data. Remember, when you compare two groups or 3 or 4 groups, you have to enter the data in SPSS in this manner only. You cannot enter that vitamin C data you enter on the first table, and vitamin placebo data you enter on the second column. That will not be allowed. Okay. Now how to compare it? For comparison, you again go analyze, select compare means. Now you have independent sample t-test. Now you have independent sample t-test. You click on that. When you click on that, you can see here two variables are there, group as well as length. So what is your test variable? Your test variable is length. So select this here. That is your test variable. You want to test length of the time. But there is a grouping variable also. You have to test the grouping variable here. Now When you select it, select your grouping variable, you can see here there are two question marks. There are two question marks. Why there are two question marks? See, the coding which you have given, 1 is equals to vitamin C, 0 is equals to placebo. SPSS don't know that coding. This coding you have given, SPSS don't know. So you have to define this coding. So group 1 is actually 1, group 2 represented by 0. So I have to define it. Whether my group 1 is represented by which number. So since I am using 1 and 0, I have to tell the SPSS that I am using 1 and 0, and then continue, and then OK. You have this output. You have this output. So you see, focus upon this output. Last one is, there is, see, equal variances assumed. So I will show you the output here, so that would be easy to understand. Yeah, length of the time could last, equal variances assumed. So equal variances assumed, there will be F-test significance. This is the t-value. You just focus upon significance two-tailed. So this is 0.072. Remember that SPSS gives you two-tailed, but your alternate hypothesis is directional. It is only in one direction. You want that placebo gets more, placebo cures in more time in comparison to this vitamin C. So it is directional. So you have to take it half of this, because it is two-tailed. You focus upon half of that. So half of that will be 0.036, which is less than 5%. So you can reject the null hypothesis at 5% level of significance. So if you reject the null hypothesis, so you can conclude that taking vitamin C 4 grams per day cures cold earlier in comparison to taking nothing or taking placebo. That is the conclusion. Okay, so my time is over, so I will take 5 to 10 minutes more if you allow me. There is only one test remain, the paired sample t-test. So what is paired sample t-test? Sometimes you have data which is paired. Which is paired means, for example, you people may have some knowledge about testing of hypothesis before attending this lecture. Okay, so if you were given a test and checked your knowledge, and after the lecture I will give you again a test and check your knowledge. So your knowledge or your marks will be dependent. So your marks before this lecture, your marks after this lecture, they are called paired data. That means data taken from same person two times, that kind of situation. So you just see this example. Suppose we are interested in learning about the effect of newly developed gasoline detergent additive on an automobile mileage. To gather information, 7 cars have been assembled and their gasoline mileages in units of miles per gallon have been determined. For each car, this determination is made both when gasoline without the additive is used and when gasoline with the additive is used. You just take it, you someone of you may be using petrol with some additive and petrol without additive. So people say that if you use petrol with additive, it will increase the mileage. So that is the idea here, gasoline with additive and gasoline without additive. Now remember, the cars are same. There are 7 cars. First car has checked for the mileage without additive, and the same first car is checked for mileage with additive. So this should be without and with. There's a typo. It says without and without in both. It should be with and without. Okay. So there is with and without. So this is the paired data. So we want to test whether there is an impact of adding additive or not. So it is easy to see that two factors. There is a car. One factor is gasoline. Other factor is car. So how to test this? So for that, I have car mileage data. I open this data. So this is the data. Now see, uh, here the data is paired. So here there is no grouping kind of thing. So you don't want to, there is no requirement to define a group variable. You just enter the data with additive and without additive. That is the idea. That is because this is the paired data. There are 7 cars. Enter the data without additive and with additive. This is the way you enter the data. Then you click on analyze. Go for compare means now paired sample t-test, because this data is paired, because car is same. You are taking two observations from the same car, one with additive and with one without additive. So data is paired. So we have to choose paired sample t-test. Now you can see pairs are there. You select first one and you select second one. So these are the variables. You click on OK. When you click on OK, you will have the output. I will show the output in my slides. So this is the output. You focus upon the output. This says that significance is 0.104. 0.104, two-tailed, because we want to test whether there is an impact of additive or not. So it is bigger than 10%. So we are not rejecting the null hypothesis. So we cannot say there is an impact. Okay. So this was the pair t-test. Now this is the summary of all the tests. This is the summary of all the tests, all the parametric tests which I have discussed today. Okay. So remember, population is always normal. Size, sample size is, if it is single and size is small or large, whatever, if variance is known, you use that test. If variance is unknown and size is small, you use t-test. If variance is unknown, size is large, you can use that test. So remember that if size is large, you can use that test. If size is small, then you see variance. If variance is also unknown, you use t-test. So these things are given. This is the summary, and these are some references which I have used to prepare the slide. First one is the paper of Booth and others. This is fetal sex determination in infants in Punjab, India, correlations and implications. This was published in British Medical Journal, volume number 309, page number these. And there is a good book, DeVox RD Wellman P Block DE, Stats, Data and Models, 4th edition. This is a very good book. If you want to learn these things, you can go through this book. And Ross SM Introductory Statistics, 3rd edition. This is also extremely good book. Extremely good book. I would suggest that all of you should go through this Ross book. This is extremely good book if you want to really learn statistics, basics of statistics. And thank you all for your patience listening. Now it's time to question and answer. If there are questions, I would be happy to answer. So if there is no question, I have to say bye-bye. So data sets, Dr. Sinha has shared. I will share my PPT also so that you can learn it by your own. And please learn it, do it, because that would be the actual workshop if you do it by yourself. So someone is asking what is the interpretation of p-value. I told you the p-value is the smallest significance level at which you can reject the null hypothesis. That means if p-value is 7%, then below 7%, if you fix your alpha, your hypothesis will not be rejected. That is the basic idea. I will share my PPT in the WhatsApp group. So if there is no question, I think I should say bye-bye to all of you and good night to all of you. We will meet tomorrow at 6. I hope the first lecture will be of mine.